Welcome to this tutorial on drawing shear force and bending moment diagram for beams. In this session, we will analyze a beam subjected to a UDL uniformly distributed load and a concentrated load as shown in this example. The beam rests on two supports, one pin and another is ruler, creating a statically determinate structure. We will determine the reaction at a support, identify the critical points, and systematically draw the SFD and BMD step by step. This example also features a point where the shear force is 0 and bending moment will be maximum, and we will use a similar triangle technique to locate it accurately. By the end of this video, you will have a clear understanding of how to approach similar problems with confidence. Let's get started. So in this example, we have this uniformly distributed load of intensity 20 kN per meter up to 4 meter from this pin support A to the ruler at point B. So we have a concentrated load of 20 kN at point C, and the total length of the beam is 6 meter. So we will be drawing the shear force diagram and bending moment diagram with a graphical method, means by area method. So the first step for all the question related to the shear force and bending moment diagram is to find the value of these reaction, the internal support reaction value. So this will be the first step for all the question related to the shear force and bending moment diagram. So we have this pin support which have two support reaction, and we have a roller which have only one reaction. So we will be naming it Rx and Ray of the pin support, and the roller at point B will be Rby. So the first step is to determine the support reaction, and this is a determinate structure because we have three unknown and we have three equilibrium equation. So the number of unknown is equal to the number of equilibrium equation, so we can easily find it by using the equilibrium equation. So the equilibrium equation are three. Number one is the summation of f of x is equal to 0, summation of f of y is equal to 0, summation of moment at any point should be equal to 0. So we will be using the first equilibrium equation, which is the summation of all the forces along x-axis should be equal to 0, and we will be assuming that all the forces along x-axis which is moving towards the right are taken as positive. So all the forces which direction is toward the right will be taken as positive, and the direction of all the forces along x-axis which is a direction along the left side will be taken as negative. So we have only one force along x-axis, so Rx equal to 0. So now the second equilibrium equation is that summation of all the forces along y-axis should be equal to 0. I am assuming that all the forces which direction is upward I am taking as positive. So all the forces which direction is downward I am taking as negative. So by doing so, Ray, so before making the equation, we have this uniformly distributed load. We will be converting it into a point load. So this uniformly distributed load will be equal to 20 into this 4. So 20 into 4 will be the end point load of this 20 into kilonewton per meter, which is acting up to 4 meter. So we will be equivalent to into the point load. We will be changing this uniformly distributed load into a point load, which is very easy by finding the area of this uniformly distributed load, which is 20 into 4. So this is converted into a point load. Now I am making the equilibrium equation which is similar, summation of all the forces along y-axis equal to 0. All the forces along y-axis which is directing upward should be in positive nature, and all the forces which is downward I am taking is in negative sign. So we have this Ray, I am writing it at positive Ray, and this positive Rby because it is upward in nature. So I am taking all the upward forces as positive. And this minus 20, which is a concentrated load, point load, minus 20 and minus 20 into 4 because this uniformly distributed load is directing downward. So I am taking as negative, and the intensity, the point load of this uniformly distributed load will be the area of this 20 into 4. So 20 into 4 will be the uniformly distributed point load of this uniformly distributed. Now by doing calculation, we have RAY plus RBY, and this minus 20 and minus 20 into 4 moving to the other side, and summing it yields 100. So RAY plus RBY is equal to 100. This will be the equation 1, because we have two unknown, so we will need further it. So we will be naming it equation number 1. Now I am taking the moment at this point or at point B equal to 0. So taking moment, it's up to you whether you are taking at point A or at point B. We will find the value of one unknown reaction. So I am taking all the moment at point A will be equal to 0. I am taking the anti-clockwise moment as positive. So remember this, I am taking the anti-clockwise moment as positive. So now here you can see that RBY, this support reaction at this A point producing the anti-clockwise moment, means positive RBY, this force into this perpendicular distance is 4. Now at this concentrated load producing the clockwise moment at point A, so I am taking as negative because I am taking the anti-clockwise moment as positive. Here it produces the clockwise moment, so minus this concentrated load, which is 20, into this overall perpendicular length, which is 4 plus 2, which yields 6 meter. So this will be the perpendicular so now at this uniformly distributed load also producing a moment at point A, which is anti-clockwise, so I am taking the anti-clockwise as positive, so it will be also negative. And this the point load of this uniformly distributed load will be the area of this rectangle, which is 20 into 4, and it acts at mid of the length. So the total length is 4. So it acts at mid, means it acts at 2 meter. So this 20 into 4 is the force, and this 2 is the perpendicular distance from A to this point, from this point to this support reaction, where I am finding the moment, summing all the moment equal to 0. So after calculation, doing the mathematics calculation, the value of RBY will be 70 kilonewton. The RBY, this support reaction value, will be equal to the 70 kilonewton. So we found the value of this support reaction. Now I need to find the value of this RAY. It's very easy, just putting in equation 1. So we will get the value of RAY. So RAY after calculation will be equal to 30 kilonewton. So this will be the first step for all the question related to the shear force and bending moment diagram. So whether you are solving by graphical method or by equation method, this will be the first step that you should find the value of the support reaction. Now we will be drawing the shear force diagram for this beam, and we have know the value of this reactions. So the Rx value is equal to 0, RAY value is 30 kilonewton, and RBY value is 70 kilonewton. So with the help of this question, we will be drawing the shear force diagram. Remember this, for graphical method we will find the shear force diagram with the help of question, and bending moment diagram with the help of shear force diagram. So we will be drawing a beam of length 6 meter here also, and a vertical line which representing the shear force value up, and this point representing the 0 value, and all the upward value representing the positive, and downward value representing the negative shear force, and with a specified unit which is kilonewton. So whether it is in question it is in kilonewton, so we'll be writing in kilonewton. If in question is it is in PS pound, so we'll be writing in pound. If in question it mentioned in kip, so we'll be writing here in kip. So the first step is that where the forces changes, draw a vertical straight line. Here only 2 points the forces changes, I am writing this vertical line, and here this dashed vertical line, here the force changes. Now we have this 30 kilonewton which is directing upward, so I will be marking this 30 and writing a straight line at this point. Here you can see that up to 30 kilonewton. Now we have plus this 30 and we have this uniformly distributed load which is directing downward. So this plus 30 minus y minus, because it's directing downward, so this 30 minus area of this rectangle which is 20 into 4. So it is very easy. The important step is that this 30 minus y minus, because it is directing downward, minus 20 into 4 the area of this UDL. So it will yield a minus 50. So I am mentioning the point minus 50 downward. So here you can see that this is a 0 degree curve, 0 degree curve, 0 degree line. So the shear force diagram will be a first degree. 1 degree is it should be increased. So by just meeting this point by a ruler, we will found this line. We have drawn this line by a line. It is a linear graph. So this 0 degree converted into as first degree in a shear force diagram. Here we have this minus 50 and we have this upward direction plus 70. So minus 50 plus 70 yields plus 20. So I will be marking at this point plus 20. So by just straight drawing the vertical line up to plus 20. Here you can see that how to draw this. Now we have from B to C we have no force. So we will move to the right without changing the curvature of the line. Means we will be moving towards the right with a 0 degree line because we have no force. So how we will do? Here you can see that we will be moving to the right at this manner. So we have this plus 20 and we have this support, this external force minus 20. Why minus 20? It is directing downward. So plus 20 and minus 20 will yield this 0. So we will be meeting this and this point by a ruler. Here you can see that. And we have drawn the shear force diagram for this particular type of beam. Here you can see that this is a point where the shear force value is 0. So how we will calculate this point? We can easily find this point by a similar triangle technique. Here this point is very important. At this point the bending moment will be maximum. So remember this. So we'll be finding this distance and this distance for by using the similar triangle technique. So I am mentioning this at this point, from this point to this point length is x, and from this point to this point is 4 minus x, because the total length is 4, and if I subtract x from 4, so I will find this mention this length which is 4 minus x. So by using the similar triangle technique we can easily find the value of this and this. So similar triangle technique says that the base of this triangle divided by the height of this triangle and the base of this triangle divided by the height of this triangle should be equal. So here you can see that the base of this triangle is x divided by the height of that triangle is 30 is equal to the base of this triangle which is 4 minus x and the base of height of this triangle which is 50. So after cross multiplying and doing calculation we will find the value of the x which is 1.5 meter. Which is 1.5 meter means this length is 1.5 meter and 4 minus 1.5 yields 2.5. So this length will be 2.5. Remember this. So from this 0 to the up to 1.5 we have a maximum moment. At 1.5 meter we have a maximum moment and a shear force 0 shear force. So with the help of shear force diagram we can easily draw a bending moment diagram. Remember this. Now we will be drawing the bending moment diagram with the help of shear force diagram. Remember this. So this length is for a bending moment diagram we need area, and for area we need dimension. So we will be mentioning all the height and base which is 1.5 meter for first triangle and 2.5 meter for second triangle, and for rectangle it is 2 meter as mentioned in the question. So for the shear force we will bending moment diagram we will do the similar as we did in shear force, that we will be drawing the beam of length 6 meter and a vertical line which mentioning the positive or negative bending moment, and this intersection mentions the zero bending moment, and with a specified unit of kilonewton meter. Now drawing the vertical line at all the points where the forces changes, whether it's at this point force changes, at this point force changes, at this point force changes. So we'll be drawing a dashed vertical lines. So here you can see that as we drawn in the SFD. So for the bending moment diagram, we need the area of the shear force diagram because it's a graphical method. So we need this area 1, area 2 and area 3. We will be finding this area. The area 1 is a triangular. Here you can see that the area of triangle is 1.2 divided 1/2 into base into height. So this is half and this is the height and this is the beam, which yields 22.5. Now for area 2, it's also similar problem. Half base into height. Base is 2.5 and height is 50. It yields 62.5. And for the rectangle, it is simply base into height, which is 20 into 2, which yields 40. So we'll be drawing the bending moment diagram. Area 1 is 22.5. So it is positive. So I will be marking this 22.5 here. So it's the first degree curve. The bending moment diagram will be a second degree curve. Remember this. So in second degree curve, we have two options, whether the curve in this manner or in this manner. So it is very important to understand. So for whenever the curve will be in this manner, second degree curve will be in this manner. If this intensity decreases, but the value is positive, means positive decrease, or here you can see that this is increases but the intensity is in negative. So whenever the positive decrease or negative increase, the curve will be in this manner. Positive decrease or negative increase, the curve will be in this manner. While for all the opposite cases, means positive increase or negative decrease, the curve will be in this manner. This is very important. If you haven't get it, write it in comment. I will be specify more. So here you can see that the graph will be in this manner. So here we have 22.5. I will be mentioning this at this point, and this is first degree. It will be converted to second degree. Now we have the positive intensity and it is decreases. So positive decrease, the curve will be in this manner. Here you can see that the curve will be this. Here you can see that this is the second degree curve. Now for this area, for second, we will be do that this 22.5 minus this area 2. Why minus? Because it is negative in nature, because it is negative. So this 22 area 1 minus area 2 will yields a second point. So we will do this calculation. It is 22.5. So for further calculation, we need to subtract area 1 and area 2. So it will yields second point at this. Why we subtracted the area 2? Because it is downward from this zero line. It is downward, so we have subtracted. So it will yields minus 40. So we will be marking a minus 40 point, and we have similar form of the graph that we have this first degree. So the bending moment diagram will be a second degree. So here the bending moment diagram will be in this manner. So we will be drawing in this manner. Here you can see that it is a negative increase. So the curve will be in this manner. Remember this. This is very important step for this example. So now we have this minus 40, and we have this area third, which is plus 40. So 8 minus 40. Why 8? Because it is from the above main line, it is positive area plus 40. So minus 40 plus 40, it yields 0. So it is a 0 degree curve. So it will be a linear graph in bending moment diagram. 1 degree increases. So we will be meeting it 8.0. So this is a linear graph. These are the second degree curve, and this is our first degree curve. So this was all about the drawing the shear force and bending moment diagram for a particular example where the shear force is maximum and bending shear force is 0 and bending moment will be maximum. Here the maximum bending moment at this point is 22.5, and we have drawn how to use the similar triangle technique to find this length, and how to draw the bending moment diagram means whether the curve is sagging or hugging in nature. So I hope you got it. If you have any question, write it in comment below. I will answer. So thanks to everyone.